Okay, Amrit, let's see how we can address your question. What you don't understand is what is the constraint relationship between this mass over here and this mass over here, right? Now, there are two ways of doing it, and the best way to sort of understand the first method, which is to figure out what happens when this moves by a small amount here, what happens to this, is by reviewing the notes that we gave you in constraint relations in the chapter Newton's laws of motion. Okay, when it comes to accelerations, which is really what is of interest here, I prefer to use another method which is also described in that same chapter, but it's faster to explain, so I'm using that method here. So here's what the important point to note is this, that this string over here, and this string over here, they're joined, right? So for all practical purposes, if I just straightened out this string, instead of making it bent here, if it were just straight like this, assuming of course that this was high enough, then we would basically have the same problem again. And that's one simplification I will make just to make the problem easier. Okay, alright, so what have we got? Here's my straightened string over here, and that's mass 1 at this point. This is pulley 2, so that's the second pulley. This is pulley 3, and this is the second mass M2. I use this point over here where the strings are attached to the top as my reference point. Okay, so this is not a string, so this is the string actually, this part and this part. This is the first string, and then the second string is really extends from here to here and here to here. Okay, now from this coordinate system, up to this point is x1, this is x1. Alright, from here to the second pulley is y1. This is what I'm defining my coordinate system as. From the reference point to P2 is this coordinate y2, and from the reference point to pulley 3 is x2. Another point to note is that because there's nothing happening with this string which connects P3 and M2, the acceleration of M2 will be the acceleration of P3. Okay, so now what are the accelerations we're talking about? So the second derivative of x1 with respect to time is the acceleration of mass 1, and the second derivative of x2 with respect to time is the acceleration of the pulley P3, which is also the acceleration of M2, and that's really the relationship that we need to find. So what can we find here? Let's look at the equations. First, this equation x1 plus y1 equals y2 really pertains to this distance, from the reference point up to pulley 2 is y2, and that's broken up as y1, which is this, and x1, which is this. Okay, so that's the obvious one. The second constraint relationship pertains to the length of the string wound around P2. So it kind of starts here, goes down here, then there's around the pulley and all the way to the top. So this distance over here, which is really y1, and that's nothing but y2 minus x1, okay, plus y2 itself is equal to L1, the length of the string. So that's the first relationship. So y2 plus this distance, which is y2 minus x1, is L1. This is our first relationship. The second relationship over here is derived by looking at the length of the second string, which is the same thing. What is the second string? It starts over here, extends down to the pulley, goes around the pulley, and then goes all the way up to the reference point. This segment, as we defined, is x2, and then this little segment here is really nothing but x2 minus y2, because this segment over here is y2. So this little segment of the pulley is nothing but x2 minus y2. So this segment, which is x2, plus this segment, which is x2 minus y2, has to be equal to L2, the length of the second string. And that's our constraint relationship over here. Now, can we use these equations to manipulate stuff? And let's see how we do that. So if I take equation 3 and multiply by 2, I get this equation, which is 4x2 minus 2y2 equals 2l2. If I substitute from equation 2, I can write 2y2 as equal to x1 plus l1, and I take the value of 2y2 here, substitute it here, and then what I get is 4x2 minus x1 minus l1 equals 2l2, and rewriting that I get 4x2 equals x1 plus 2l2 plus l1. Okay, just simple algebraic manipulation. Now I differentiate both sides. Differentiating first time, I get this because the differential of the constants cancels out. So 4 dx2 by dt is equals dx1 by dt. Differentiate a second time, 4 d square x, and I'm sorry, this should be 2 over here, so I'll write that. So 4 d square x2 by dt should equal d square x1 by dt squared. And you know that this term is nothing but a2, this term is nothing but a1, and that gives us the relationship that we're looking for to solve the problem. Let me know if that works or if there's any confusion.